This is part 5 of the series Three-Dimensional Solids, and we're going to start this part with an example of how to calculate lateral and surface area of a rectangular pyramid. So take a look at this problem. We're given the height of the pyramid and we're given both slant heights. Now the fundamental issue here is in order to find the area of this triangle and the area of this triangle, we need to know the lengths of these bases. And that's not given to us right up front. So what we're going to have to do is we're going to have to use the information given to create it. Now if you notice, this height is perpendicular to the base. And so what I can do is I can draw a segment in here, creating a right triangle. I can also generate another one here, creating a second right triangle. So here we have two right triangles that we should be able to solve because we have a leg and the hypotenuse of this right triangle, and we have the leg and hypotenuse of that right triangle. Now, if you notice, with this side being 8 and this side being 17, this is an 8, 15, 17 Pythagorean triple. So this side length is 15. If you couldn't see that, that's okay. You can just use the Pythagorean theorem. Let's just call this leg X and this leg Y. And so we know that X squared plus 8 squared equals 17 squared. And we want to solve for X. X squared equals 17 squared minus 8 squared. Take the square root of both sides. So X is equal to the square root of 17 squared minus 8 squared. That equals 15, as we already said. Now this triangle in here, this is also a Pythagorean triple. This happens to be a 3, 4, 5 right triangle with a multiple of 2. So since this is 4 times 2, 5 times 2, this has to be 3 times 2, which is 6. So we know that since this is X, Y is going to be equal to 6. So this guy is 15 and this guy is 6. Now that makes this side length twice this length. So this length is 30 from here to here. And since this is 6, this whole length is 12. So this distance is 12. And now we have everything we need to find our lateral area and our surface area because we can find the area of that rectangular base. So let's go ahead and calculate that. We know that the area of this triangle, we'll call this T1. We'll call this guy T2. So the area of T1 is 1/2 base, which is 12, times height, which is the slant height, 17. And then area of T2 is 1/2. The base in this case is 30 times height 2, which is 10. So that guy is 102. And if we put this in our calculator, we get 150. So we have the area of this triangle and the area of this. Now we can find our lateral area. The lateral area is going to be equal to area of T1 times 2. So it's 2 times area of T1 plus 2 times area of T2. And that equals 2 times 102 plus 2 times 150. And that whole thing comes out to 504. Now we can do our surface area. So surface area is equal to lateral area plus big B, which is the area of the base. And that gives me 504 plus area of the base is just 12 times 30. Which is going to equal 864. Now, as you can see, it's not all that terribly difficult. The big issue at this point is just understanding that you'd had to find this dimension and this dimension. And it always helps to have a good understanding of the basic tools that you have, in this case, the Pythagorean theorem or the Pythagorean triples memorized. So that's how to do a standard rectangular pyramid. You might not encounter these all that often, but when you do, it's good to know that you can do it. Alright, let's move on to the next topic. We're going to look at the surface area and lateral area of cones. Here we have two cones. The top one is what's known as a right circular cone, and it's called a right circular cone because the segment from the vertex of the cone to the center of the base, we'll call that the axis. That axis is perpendicular to the base. That is a right circular cone. And it's a circular cone because the base is a circle. This would be the radius, this would be the height, the axis length is the height, and this is the slant height. Very similar to what we had in pyramids, where it was the diagonal distance from the vertex perpendicular to a base, to the center of the base. In a pyramid, here it's the slant height. It's the perpendicular distance directly down along the side of the cone. Now, this is an oblique cone, and it's oblique because the axis, you see, is no longer perpendicular to the base. And one of the things you'll have to be conscious of in oblique cones is the determination of the height of the cone, because it's not always obvious what the height is. It's clearly not going to be the length of a diagonal segment. It's going to be an altitude from the vertex directly down perpendicular to the radius. It may be inside the cone, it may be outside the cone. You'll just have to determine on situation by situation basis. Now, before we look at any formulas for lateral area and surface area of cones, I think it's important for us to take a look at the net of a cone, because to see how this cone unwraps is going to be critical in determining how we derive a formula for the lateral area and surface area. So let's go ahead and take a look at the net of a cone. Now, here we have a typical cone with the base and the nape of the cone. And what I'm going to do is I'm going to start unfolding this, and I want you to notice what happens as the nape separates from the base of the cone. So we're going to go ahead and start unwrapping this, and you'll see that, notice how the nape of the cone here is separating from the base, but notice this distance around the nape of the cone. As I continue to expand that, you can clearly see that this piece, this distance from here to here, is the distance around the base. So you can think of the circumference of the base as the length of this arc from here to here. And as we finish expanding this, you can see that this distance is an arc length, and that arc length is equal to the circumference of the base. And this whole piece, the nape of the cone, this nape is unfolded into a sector of a circle with a specific angle in here. And the critical difference is this distance from here to here. Notice how this circle if we extend this all the way around, this circle would be much larger than this circle in this particular case. That distance is that distance from here to here. It's the slant height of the cone. So what we have is the sector of a circle with a radius equal to the slant height. So that is going to be our lateral area for our cone. So the lateral area for a cone is going to be the area of this sector. And it's the sector of a circle with a radius equal to the slant height, and this arc length equal to the arc length of this sector given whatever this angle happens to be. So using this information, let's go ahead and build some formulas for lateral area and surface area of a cone. Here are the formulas for lateral area and surface area of a cone. Lateral area looks fairly simple. It's kind of cryptic though. Pi times radius times slant height. That's the lateral area, the area of this sector, which is the area of the nape of the cone. And the surface area is a simple familiar formula, lateral area plus big B, which is the area of the base. Now let's take a look at the derivation of this because I think it's important. The radius of the base is here, and the slant height is the radius of this sector. Now, as you remember from the last unit, the area of a sector of a circle is given by this equation. Area of a sector is to the area of a circle as the central angle is to 360. And the arc length formula was very similar. Arc length is to circumference of the circle as the central angle is to 360. Notice how both arc length and area of sector are both equal to the central angle over 360. So we can do a substitution here and substitute this for this. So we can see that area of the sector is to the area of the circle as arc length is to circumference. Now putting it in terms of this image here, we know that the arc length is this distance, which is simply the circumference of the base. And that's going to be 2 pi r. So the arc length is 2 pi r. Now the circumference of the sector of our circle, the circumference of this sector is 2 pi r, and the radius of this circle is the slant height. So this 2 pi r gets changed to 2 pi l. And the area of the sector is to the area of the circle. The area of the circle that has our sector in it is pi r squared. Well, again, the radius is simply this slant height. So this pi r squared gets changed to pi l squared. So we have area of sector is to pi l squared as 2 pi r is to 2 pi l. Well, notice the 2 pi's here will cancel out, and what we have left is r over l. Now to solve for area of the sector, of course, is the lateral area of our cone. That's the area of this sector here. That's all we have to do is multiply by this denominator. So we multiply both sides by pi l squared, and we have this expression here. Area of sector equals pi l squared times r over l. Well, there's an l here and an l squared here, so this l goes away and one of these l's go away, and we're left with area of sector is pi r l. So that gives us lateral area. So the area of this piece is pi r l. And to complete the surface area formula, we take this pi r l and add to it the area of the base, and this base is going to be a circle, so that's just pi r squared. So surface area is lateral area plus area of the base, or pi r l plus pi r squared, and lateral area is just pi r l. Now I know this is quite a bit to absorb in a short period of time, so if you need to review the video again, please do so, but it's important to have these ideas in your head before you move on. And so that'll pretty much wrap it up for this video, and in the next video we'll go ahead and work some examples. So I will talk to you again in the next video.